Hello and welcome to another Dante tutorial. Today I'll be showing you how to set up a gas carburizing simulation in Ansys using Dante. The Dante software package integrates directly into Ansys and includes the necessary Dante subroutines along with an Ansys ACT extension that makes building heat treatment models much easier. By the end of this video, you'll understand how to use these tools together to create a full gas carburizing model. First, let's open Ansys Workbench and set up our working directory. Create a working directory. I'm going to save the Ansys Workbench file inside my prepared folder. Once we set the working directory and save the project, we can drag over the mechanical model under Component Systems so we can build our geometry. For this model, we're going to assume symmetrical boundary conditions and create just a slice part instead of a full ring. This will save some computational time, which might be significant, especially for larger models with more steps. If you have a CAD file, you can also import the file here instead of having to build it by hand. Right-click Geometry and click Design Modeler. Once we have the design modeler open, we can click New Sketch and a sketch should appear on the XY plane. For this tutorial, we're going to be modeling a gas carburization process for a ring with an inner radius of 10 millimeters, outer radius of 20 millimeters, and a height of 20 millimeters. Since the Dante subroutine only takes millimeters, seconds, and kilograms, let's change the units before we build our geometry here by clicking the units up at the top. We can click the sketch over and go over into the sketching mode. Let's select the rectangle option next and draw a rectangle in the first quadrant with the approximate dimensions. Now we can go to dimensions and click general. Once we have general selected, we can click on the vertical and horizontal line to change the dimensions of the line. The vertical line should be 20 millimeters and the horizontal line should be 10 millimeters. Those are our dimensions set and our sketch created. Any more dimensions will overconstrain the part. Since we are modeling a slice, the next step will be to revolve the part 10 degrees. To do that, we can go to Create and select the Revolve option. This should create Revolve 1 in our tree and give us the details view down below. For the geometry, you can select Sketch 1. For the axis, select the Y-axis, and for the angle, change this to 10 degrees. Once we have those options set, we can click Generate. Now you should see one Part 1 body in your tree. Now that we're done with the geometry, we can close this window and proceed to the next step. Select Model. This is where we are going to be creating the mesh for this model. For the mesh, the general rule of thumb for a heat treatment model is to create a thin inflation layer on the exposed surface of the part so that we can accurately capture the carbon and temperature gradient for the different models we're going to build. This temperature and carbon gradient will have a significant impact on the phase transformations, stress, distortion, and other results for the model. If your elements are too coarse, you won't be able to accurately capture the behavior of the part in your model. Luckily, it's easy to adjust this mesh if it starts looking weird. The first thing we want to do is create a named selection for the outer surface. This surface is what we're going to use to create the inflation layer and the surface we're going to apply boundary conditions to. So let's select the surface by holding Control and clicking the outer surfaces. After selected all four surfaces, we can right-click and select Create Name Selections. I'm going to name this Outer Surface. Next, if we go to the mesh, we can select the inflation option, select the entire part as the geometry, and the outer surface selection we just created as the boundary. For this video, we are going to use first layer thickness as the inflation option. This means we get to define the first layer height, maximum layers, and growth rate. For a gas carburizing model, typically we start with a thickness of between 0.1 to 2 millimeters at the surface. For low pressure carburizing and especially nitriding, you will have to use a smaller first layer thickness. The maximum layers and growth rate will typically depend on the case depth. If we have a case depth of 10 millimeters, then the total thickness of the inflation layer will need to be at least 10 millimeters. For this mesh, we're going to use 0.15 millimeters, 7, and 1.2 for growth rate. Next, we can go back to the detailed page of our mesh. For physics preference, instead of mechanical, we'll use CFD. This gives a slightly better quality inflation mesh that we are looking for, especially near the surface. For simple geometries like this, either option will work. Next is the element size. For this example, we can probably leave this as default. The element size here controls the element size for the rest of the part outside the main inflation layer. For more complex geometries, there are different global mesh settings that you can use to control the growth rate, which is how fast the mesh grows to the global max. And you can also change the element size at curvatures, which is important for complex geometries with fillets and other features. For this part, we'll leave the rest of the options as default and click Generate. For the purposes of this tutorial, this mesh we generated is probably good enough. You can always go back to the mesh settings and adjust different options to get a finer or more coarse mesh for your model. Now that we have our mesh created, we can close out of this window and let's save our project again. I'm also going to turn Dante on by going to Extensions, Manage Extensions, and clicking the checkmark next to Dante Act. The next step is to create our carburizing model. To do this, Dante takes advantage of the heat transfer from the transient thermal model in Ansys. Next, we can link the model from the mechanical model to the transient model to pass our mesh and name selections over. Then right-click Model under Transient Thermal and click Update. Now we can open the transient thermal model by double-clicking Setup. Once we have the thermal model open, let's make sure the part, mesh, and name selections loaded in correctly. We see our part here, and the mesh looks correct. If we expand the name selections, we can see our outer surface we created earlier. Now, up at the top, let's click the Dante tab and select Carburization under Dante Model. Next, let's click on Initial Temperature on the model tree and change the initial temperature to 0.002. This will represent the base carbon content of the material. As previously mentioned, the Dante package takes advantage of the transient thermal model by using temperature as carbon. This is possible because of Fick's law for carbon diffusion, which is very similar to convection coefficient equation. Next, we'll define the processing steps and analysis settings. This is where we will define the carburizing steps for the two-step carburizing process we are going to model. Let's change the number of steps to 2, and we'll be starting with step 2, since this way we can define the step time by the end step time. I'll be using these numbers here to fill in for the step end time, initial time step, minimum time step, and the maximum time step. Also be sure to turn on the time integration, and make sure the nonlinear formulation is set to full. Once you have those filled out, We'll go to the first time step and do the same thing with these numbers, also making sure time integration is turned on and the nonlinear formulation is set to full. Now we can go back to the Dante tab and start applying the Dante conditions from left to right. We'll start with material. Select the whole body as a geometry and use the S10XX material. In this case, we're going to be modeling a double carburizing process for a 1020 grade steel. Next, let's define the carburizing temperature. Adding 4 rows, with the first 2 rows will be the carburizing temperature for the first step, and the second 2 rows being the carburizing temperature for the second step. The carburizing temperature we'll use is 925 Celsius and 875 Celsius. After we apply the temperature, we click Apply. Next option after that is the model control. For a carburizing model, the model control option is max carbon change per substep. Too large of a value results in inaccuracy, while too small of a value and the model might take longer to run. Typically, we can leave this value as default at 0.0005. The last option we have to define is the output frequency. This controls how often the results are saved. An output frequency of 10 means results are saved every 10 substeps. An output frequency of 1 means the results are saved every substep. For this model, we'll leave it at 10. Now, to apply the boundary conditions, let's click Transient Thermal in the model tree and select Environment in the tab above. Since the Dante carburizing model replaces temperature with the carbon value, we can use the convection coefficient to model the carbon surface reaction. The carbon reaction basically controls how quickly carbon is transferred from the atmosphere into the steel surface. The value is dependent on the equipment used, but a value of 0.005 is good enough for most carburizing processes. We can click Convection. I'm going to rename the carb step 1. And then click the outer surface now under the name selection. Let's change the film coefficient to 0.005 and 0.011 for the ambient temperature to represent the carbon potential. Now, since this only applies to the first step, let's change the step 1 time to 14400 and then disable step 2. Let's go through the same process for the second step. Now, before we solve, we should also write out the carbon profile so that we can import other models like the thermal and stress model that we can build later. Now we can finalize the model settings so that the Dante control saves and runs a simulation. Now it's time to run your simulation. Right-click Solution in the model tree and click Solve. This may take a few minutes or even longer depending on the size and complexity of your model. Once Ansys says ready at the bottom and has a green check mark next to solution, that means your simulation is ready. We can now take a look at the different results. We can look at the written results under solution information in the model tree. We have the temperature, which is really carbon. We can take a look at total carbon. We can also include alloy precipitates that might have formed, or even just the alloy precipitate alone. We can go to Carbon All and click play to run the simulation to see how, over time, the carbon penetrates the surface. We can also create a cut section view by going to the Home tab and clicking the section plane. Click New, and then drag a line across the model. And this concludes the Dante Ansys gas carb tutorial. Thank you for watching, and if you have any questions or want to learn more about the Dante software, please visit www.dante-solutions.com or send us an email at support@dante-solutions.com.